we have finished the review about sea-level laser theory. Now it's about mathematics, review of Fourier transform. This is a very useful tool in this subject. So I will show you the definition of Fourier transform and some important properties and the corresponding interpretations. I prefer not just being stick to the formulas. I need to give you some interpretations. Okay? Definition. I think you have seen this before. A temporal function, small f of t, and a spectral function, big F of omega, are Fourier transform pair if they follow these two formulas. Okay? Big F of omega is equal to small f of t times the kernel function, e to the minus j omega t, then integrated over the entire time axis from minus infinity to plus infinity. Okay, so this is the Fourier transform formula. And the next one is the inverse Fourier transform formula. Small f of t can be obtained by a similar integral where the integrand is the product of the spectral function big F and the kernel function e to the positive j omega t. Okay? I'm sure you have been familiar with the formulas. But the question is, what is the meaning of these two formulas? Okay? Are they just two formulas torturing the students? Of course not. I use this simple figure to show you what is the idea underlying the Fourier transform theory. So this is a very easy geometry. Okay? Say you have a vector on xy plane. The vector is the blue arrow shown here. And you have known this blue vector can be decomposed into x and y components, right? The x component or projection is x0, y projection is y0. Then this vector can also be represented by a pair of two numbers, x0, y0. Okay? So what's the relation between the geometry, plane geometry, to Fourier transform? Okay, my interpretation is, let's look at the second formula, the inverse Fourier transform formula. It states that f of t, the time domain function, is superposition of many orthogonal functions e to the j omega t, right? You see integration, which is the generalized summation, right? So f of t is the summation of many e to the j omega t. Each one has its specific frequency omega, right? If you sum them together, you can synthesize f of t. So equivalently speaking, f of t is similar to the blue vector here. And the e to the j omega t, omega equals omega 1, omega 2, and so forth, are similar to the x, y, maybe z, or even more axis, right? And the big F of omega is similar to the projection numbers x0, y0, and so forth. Okay? Just like x0, y0 describe the projection of the vector on orthogonal axis. Big F of omega specifies the projection of small f of t on different orthogonal functions, e to the j omega t. Okay, so you can see close relations between Fourier transform and the geometry. The only difference is here you have only two basis vectors or two orthogonal axes. Here, how many do you have? Infinitely many, right? The only difference is like this. Okay. Any question? Good. Now we can talk about the Fourier transform properties. Okay. We will use these properties frequently in this subject, so it's very helpful to review them at the beginning. First, reality. If time domain function is a real function, then the spectral function has to satisfy big F of minus omega equals big F of omega star. Star means complex conjugate. Okay? I skip the proof. You can practice by yourself. But this is the result, which can be proven easily. Okay? But if you stop here, it's kind of unclear. What does this mean? So let me interpret this relation in this way. This relation means two things. First, if you check the magnitude function, it's even function. If you check the phase function, it's an odd function because of the complex conjugate, right? So if you take absolute value, complex conjugate doesn't matter, so you got even function. F of minus omega absolute value equals F of omega absolute value. It's an even function. But if you look at the phase function, you got an odd relation. Okay? We will use this property soon. The second property is scaling. If you try to calculate the Fourier transform of f of at instead of f of t, a is a positive constant. Okay? Then you will get something like this. The Fourier transform is proportional to big F of omega over A instead of big F of A omega. So, for example, A equals 2. What is F of 2t? Compression along the time axis by a factor of 2, right? Then the corresponding spectrum is big F of omega over 2. What is that? Expansion along the omega axis by a factor of 2, right? So if you compress in time domain, you got expansion in the frequency domain. And they share the same ratio, right? So this is sort of the uncertainty principle in physics, right? What is uncertainty principle in physics, in quantum physics? If you try to push the accuracy of position, that means along the position axis, the uncertainty is very small, then you have to pay the price on the momentum axis. You got a very broad uncertainty. Okay, so it's very similar to the scaling relation in Fourier transform. We will also use the scaling property soon. Third, the time delay. Let's try to calculate the Fourier transform of f of t minus tau. What is f of t minus tau? The original function shifted by tau along the time axis. Everything is the same, but shifted by tau. Okay? And the corresponding spectral function is the original one, big F, multiplied with e to the minus j omega tau. Okay? But remember, the variable is omega. Tau is a constant. So how do you interpret this modulation function? If you check the magnitude, what do you have? Constant 1. Nothing changed. So there is no amplitude modulation at all, right? But if you check the phase, what is the phase? What is the phase corresponding to e to the j omega tau? Phase means something on the exponent, but imaginary part, right? E to the j theta. Theta is the phase. So in this representation, what is the phase? E to the j, everything else is the phase, which is minus omega tau, a linear function of omega, right? So it's called the linear spectral phase modulation. So simply speaking, a shift in the time domain is equal to a linear phase modulation in the frequency domain. Okay? So that's the interpretation. And you can have a very similar counterpart, frequency shift. Okay? This time, if you shift the frequency domain function by an amount of omega 0, what do you have in the time domain? Very similar to the number 3. This time, you have a pure phase modulation in the time domain, and it's also a linear phase modulation because your phase is omega 0 constant times linear function of time, t. Okay? So you have a linear temporal phase modulation to be performed such that you can have a frequency domain shift. So property number 3 and the number 4 are just the counterpart. Okay. Number 5, convolution. Okay. Do you still remember the formula about convolution? If you have two functions, f and g, in the time domain, what is the convolution? It's shown here, right? I think the formula is not difficult, but do you still remember the meaning of the convolution? It's about the linear system theory, okay? I think you can review the convolution by yourself, but let's check the Fourier transform of convolution. The result is quite easy. You have multiplication in the other domain. Convolution in the time domain is equivalent to multiplication in the frequency domain, or vice versa. Okay? Oh, sorry. Number 6, temporal comb corresponds to spectral comb. What is comb? What is a comb? You use a comb to deal with your hair, right? So basically, a comb function means a periodic delta function, like this. Sigma delta of t minus nt. N is an integer. So it means you can imagine this temporal comb function is a series of delta functions uniformly spaced by big T. Big T is your period, okay? For every period, big T, you got the delta function. And it's an infinite extension. If you try to calculate the Fourier transform of this strange function in the time domain, you got a strange result. In the frequency domain, you have the same shape, a series of delta functions in the frequency domain. But the spacing is changed from big T to delta omega. And they are related by delta omega equals 2 pi over big T. Okay? The mathematical proof is quite interesting. I encourage you to practice by yourself. But the result is strikingly surprising. Okay? A comb in the time domain is equivalent to a comb in the frequency domain. But because of the relation that you can easily sense, if you reduce the period in the time domain, you have a smaller big T, you have a denser delta functions in the time domain, what do you have in the frequency domain? Your spacing delta omega becomes bigger. That means your frequency comb is less dense, right? Peak to peak spacing is increased. So if you compress the comb in the time domain, you got expansion in the frequency domain, consistent with the scaling relation we just talked about, right? The last one is the well-known Parseval's theorem. If you integrate the absolute square of the time domain function, you can also arrive at the same result by calculating the integration of absolute square of the frequency domain function. And the physical meaning is conservation of power or conservation of energy. If you assume f of t is something like electric field, what is the corresponding absolute square? Field, absolute square. What do you have? Intensity or power, right? And if you integrate power function with respect to time, what do you have? Power means energy per unit time. Integration with respect to time, you got energy. From minus infinity to plus infinity means total energy, right? And the total energy should be conserved, no matter you observe it in time or frequency domain, right? So you can easily understand that the meaning of big F absolute square is the power within a small interval of frequencies. Okay, so power per unit frequency per unit bandwidth. Okay, if you integrate all the frequencies, you also got the total energy. So that means big F of omega absolute square is the so-called power density, the power per unit bandwidth. Okay, power density. It can be easily proven by yourself as well. So we can move on to the last subsection, pulse formation via Moore locking. Okay, so finally we can talk a little bit about the generation of short pulses. Okay, so far we only talk about CW lasers, nothing about short pulse. Okay, now we can have some idea. Starting with carrier envelope representations, and then the definitions of laser intensities, and eventually the impact of phases on pulse formation. First, we can compare the difference between CW light and the short pulse. What is CW light? In the time domain, you have a constant intensity, but in the frequency domain, you have a delta function, right? And it's mathematically true. The Fourier transform of a constant function is a delta function, as you have studied before. So this is the case about CW light. How about the short pulse? Got the reverse. You have a delta function in the time domain, ideally, right? And what do you have in the frequency domain? By mathematics, you know you have a constant. But this constant tells us two things. Okay? It's constant in terms of both amplitude and phase. Remember, the frequency domain function, big F of omega, in general is a complex function. It's not a real function. Even your time domain function is real. Your frequency domain function in general is complex. And if you want to specify a complex function, you have to specify both amplitude and the phase. So Fourier transform of a delta function in time domain is a constant in the frequency domain, but this constant simultaneously means it's constant in terms of amplitude and the phase together. Okay? That this simple figure already tells us how do we generate a short pulse. Okay? You have to meet two requirements. First, you need a broad bandwidth, right? Broad constant amplitude. Secondly, you need phase locking. All the frequency components here, 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 here have to share the common phase. If you only meet one of them, you cannot get short pulse. Say you have broad bandwidth, amplitude is constant, but your phase is random. Then in the time domain, it's no longer a delta function. You have a broadened waveform in the time domain. Okay? So we have already know the keys to generate short pulses. Okay? Broad bandwidth and the phase locking. Okay? You will see the same conclusion later.